It's going to be an interesting lecture today. First thing first, I owe you an extra lecture, please, and maybe I'll add more just because we want to do kosmology. So you mark here, made a short table specifying where we need to find a time that is suitable for everybody. Right? So to do that, what's going to happen is that you're just going to write down any time that is not possible for you. Just put an X. Then we'll see if there is any left over without X's. Okay, so don't say what is good for you, just say if it is impossible for you, just put an X. Okay? At the end, we'll see what is left. Okay. So we're talking about the principle of equivalence. And its consequences. See here. So we said there are two equivalence principles, really, right? One is the weak equivalence principle. This is Bosch's experiment. Weak equivalence. It's a recap. Equivalence principle. This is what Bosch experiment. So that the inertial mass is equal to the gravitational mass. Again, this is far from being trivial. In electromagnetism, inertial mass is inertial mass, right? And mg, what we call gravitational mass, is the coupling to the gravitational field. Right? The coupling in electromagnetism to the electromagnetic field is the charge. Right? And the charge and the mass are not the same. Right? Then there is a strong equivalence principle, which essentially says that at every point in arbitrary gravitational field, we can always find a locally inertial coordinate system. Right? So, strong equivalence principle. Principle. I should not write it down, I just mention it again. At every point in arbitrary gravitational field, it is possible to choose a local inertial coordinate system such that within a sufficiently small region of the point of interest, the laws of nature takes the same form as in special relativity. Okay, we'll write it. At every point in arbitrary gravitational field, it is possible to choose a locally inertial coordinate system. Such that the laws of nature takes the same form. Take the same form. Same form as in unaccelerated. That's basically the elevator experiment. Yes?
After some frictional acceleration, right?
What?
After some friction, we get some frictional acceleration. What we did in this.
What do you mean frictional acceleration?
We had this, we assumed this system in the gravitational field is described like a system in the same acceleration going up. It's sitting in an accelerating.
What this states is that in every location in arbitrary gravitational field, there's always a free falling system.
Okay, but the free falling system is
free falling in which you don't feel the gravity. Right? You're in an elevator, somebody cuts the cable. Now you're falling.
But you do have
and you try to measure gravity and you cannot.
Okay.
That's what it says. What I said, this is exactly an analog to the instead of being in a gravitational field, being in an accelerated system. Right? It's exactly the same thing. But the way the equivalence principle is formulated is the elevator experiment, basically. Okay. There is always a freely falling coordinate system. Further questions? No? Okay. Then we saw that this by itself is sufficient to give rise to the gravitational redshift. Right? As a signal tries to get out of the gravitational potential, it's being redshifted. Right? Nu infinity. Right? If there is a star, which is a typical situation that emits radiation, right? Our sun emits radiation. We are the observer, we're somewhere at infinity. Right? Then the observed frequency, nu infinity, is nu star 1 minus gm over r c squared. The radius of emission. The mass of the sun, the star. Right? We don't observe the same frequencies as millimeter. Then we moved into mathematical description. Now, these are things that are very easy to get confused in. I'm trying to be very precise on where we're doing math and where we're doing physics. Okay. Mathematical prescription of course space-time. So we start with a freely falling coordinate system. So v tau squared in freely falling system. V tau squared is minus over c squared eta mu d psi alpha d psi beta. And then in arbitrary coordinate system, minus 1 over c squared dm g eta alpha beta. G mu nu dx mu dx mu, arbitrary coordinate system. Where G mu nu was defined as eta alpha beta d psi alpha over dx mu d psi beta over dx mu. That's also called the metric tension. Okay. This is a freely falling system, xi. This is any system.
So
yes.
In the equation of the gravitational redshift, what's that? Like it looks like a power. I don't think.
So it's like a what?
Like above the brackets.
You mean that? That was the observer. Then we looked at the free particle, motion of a free particle. So here it would be du alpha over d psi is equal d squared. Sorry, du alpha d tau. D squared psi alpha over d tau squared is equal to 0. And in arbitrary coordinate system, this was d small u here, u lambda over d tau plus equal to minus gamma lambda mu nu u mu u gamma lambda mu nu minus dx lambda over d psi alpha d squared psi alpha over d x mu dx nu.
We also had the
This is called the affine connection.
we also had the formula for the affine connection in terms of G.
Is there a question?
We have the formula for the affine connection in terms of
I'm going over now as a quick recap of what we did last lecture. This is known as the geodesic equation. And then the last thing I did was really showing to you the relation between the affine connection and the metric tensor. And we derived the formula that the affine connection, lambda sigma lambda mu, gamma sigma lambda mu is 1/2 g nu sigma dg mu nu dx lambda plus dg lambda nu dx mu minus dg mu lambda over dx. So in order to get so basically once we know the metric, we know what is the affine connection, we just need to inverse the metric and first derivative of the metric. So if we interpret the affine connection as responsible for the acceleration due to gravitational force, that means that the metric would be associated with the potential. This is a physical interpretation. Right now we're just talking about pure math. This is generally true, and I gave you a final example showing that this can work out in any coordinate system, even when you write pure, simple Euclidean system, but you don't have to write it in Cartesian coordinates. And the last thing I said, this also has another name. This is called the Christoffel symbol, and the notation is Christoffel, which is sigma lambda mu. Now the Christoffel symbol or the affine connection is not a tensor. That's why I write it with one upper index and two lower index above it, as opposed to what I would do when there is a vector tensor. Any questions? We'll get the next problem set today, just to keep you busy over the weekend. Too bored. I knew it happened.
We also have the second.
Yeah.
Weekend.
How is that?
Very fun.
What's the big deal? Okay. Questions? Okay. So we're going to do today a few things. The first thing is going to be very relevant for the next. It's semi-physics, semi-mathematics. More physics than mathematics. I'm going to argue. We said this equation is the geodesic equation, right? This is a very important equation because it describes the motion of a free particle, right? Freely falling particle, namely a particle that does not have any forces acting on it. What does it mean, any forces? Gravity is not a force, right? So there's no electromagnetic force, there's no nuclear force, there's no any other force that we know of in nature, but gravity, right? Because gravity is not a force. What is the now we're going to physics again. What is the motion of a free falling particle if we have no force acting on a particle?
Straight line.
It's a straight line, basically, right? What is the generalization of a straight line? What? Well, yeah, geodesic, yeah. Essentially, yes. Geodesic, when people speak about geodesics, you might have heard the term geodesics, right? Mainly when you speak about yeah, it's a mathematical term. Basically, this is the generalization of the concept of a straight line, right? Now, since we're physicists, we go slightly beyond that. Straight line is really the shortest path between 2 points, right? So we have 2 points, and lacking any other forces, the path that the particle will take is a straight line, which is the shortest path. it's extremal, but the way we derive it is extremal, right? It's really a minimum. But the way it's being derived, how do we derive it? How did you derive these things? Heshbon variatzia, variational calculus, right? Is there anybody who did not take mechanics, second year mechanics? No. So you're all familiar with variational principle. Okay, good. I'm more relaxed. So that's what we're going to do now. I'm actually going to show you. That's kind of the connecting part between the physics and the math, or the math and the physics. I'm actually going to show you that we can get to the same equation, the geodesic equation, which is written here, from variational principle. Okay, so you'll see that it's not. It has a deeper meaning. So let me just write it down. So the geodesic equation du lambda over du tau is equal to minus gamma lambda mu to u mu u. So it's not particularly difficult if you're familiar with variational principle, then it's actually pretty straightforward. But yeah, we'll do it just to refresh your memory. Geodesic equation and variational principle. So again, variational principle is relevant as long as we're considering a test particle, right? What does it mean, test particle?
Moves but doesn't really.
What?
Particle that moves but doesn't really move or something like that.
No, moves.
Maybe a particle that moves but doesn't affect the other.
Exactly. So particle that I can neglect its gravitational field, right? Every particle has a gravitational field. But if you think of a spaceship that moves in the gravitational potential of the Earth, for example, gravitational potential that the gravitational force that the spaceship exerts on Earth can be neglected, basically. Right? That's what it means. So how big is a test particle? That depends on the system, right? The Earth's gravitational field can be neglected relative to the sun's gravitational field, for example. Right? So we can consider as a test particle in the sun's gravitational field. Okay. So motion of a test particle. Right. Really falling. And we said that the particle takes the shortest path. Between points A and B, in the sense that it minimizes. What does it minimize?
The distance.
Time.
What time?
Proper time.
The proper time, right? Minimizes the proper time between points. this is basically generalization of the concept of straight line. Question?
About the geodesic equation.
Yeah.
In general, as the particle moves, its critical coefficients will change, right? Because it moves, so in 2 points, we have different gravitation and therefore different metrics. Yeah, okay. And you, all these vectors are living in a tangent space to the points in time, which is in the time, right?
Yeah. That's true. That's the next thing we're going to do. We'll start it today, I hope. I hope we'll have some time today to start discussing curved spaces. More general. Okay. So we'll start by the simplest part, the special relativity, right? Special relativity is easy. Right, so equation of motion of a free particle in special relativity from variational principle. So the path, that basically answers your question, I think. The path, the time, the proper time that it takes to reach from A to B. What is that? Is an integral from A to B of the tau. Don't look at me like that. It's equal to what? Well, you know what is the tau? It's actually was written here somewhere. Integral, let's say the lambda. This will be our path, right? It's minus 1 over c squared. Eta alpha beta d psi alpha over d lambda d psi beta over d lambda. Or 1/2, because that's the way I derived it. What is lambda? It's a parameter, right? Along the characterizes the path of the particle. I don't need the g here. I got the meta. It's a special relativity.
No, the expression looks like it. No.
Yeah?
Yeah.
That's what's in here. So what do we want?
What are the limits of the integral? The
What?
new integral. What are the limits?
From A to B.
No, the new integral. Are they still?
It's the same. It's
Yeah,
the same thing.
okay.
The tau is just a path. Just a path. A path. The tau. Just wrote the tau as the tau the lambda. The lambda.
A and B have units of time, and lambda is the
Oh no.
number.
There's a no instead.
values of the parameter.
What? It's a parameter. The lambda is the parameter. Okay, you're right. Sorry, you're right. It's a parameter. You can decide lambda equal to 0. That is A. Equal to A. Lambda equal to whatever. Choose a number. E. 3. Tau equal to B. Right. So that's why I didn't write it in the first place. Okay. Whatever you want.
So it depends on how we define the lambda.
No, lambda is just a parameter along the path, along the curve.
Okay.
That's point A, that's point B. Right? The particle is going to travel from A to B. It has multiple passes. That's one pass, that's another pass, that's a third pass. Right? You go in various passes from A to B. Right? I argue that now we can say, okay, this is tau equal to whatever, 0. This is tau equal to something. So I can specify now a parameter lambda along the path. That's going to be a standard thing we're going to do. We're going to use it quite often because we need to, when we work on manifolds, we are stick to the manifold. So we need to do things, we can only work with things that are on the manifold, not outside of the manifold. The Earth is a sphere, right? But from a point of view of an ant, how can the ant know it's a sphere? The ant, today we can say, oh, no problem. When I send an astronaut to the International Space Station or to the moon, we take a picture and say, ah, here's a sphere. But no, I'm an ant. You too. And the ant is stick to the surface of the Earth. It cannot go outside. There's no way to go outside. The ant needs to be smart enough to deduce that the Earth is not Euclidean space, but rather a sphere without getting out of there.
It can go in a triangle and measure the angle.
Depends how smart the ant is, but yes. Right? So the idea is that we can go on a hike along the path, right? So the hike, I can know travel, and I can specify where I am on the hike by a parameter which I call lambda. Okay, so lambda equal to 0, 1, 2, 3, 4, 5, things like e, whatever you choose. Okay? There's another path, right? This is also a path. I can choose to go along this path. It's fine. I can choose whatever path I want. Lambda specifies where I am along the path. Yeah? Yeah?
No, but if it should be lambda in the path, in the shortest path.
Oh, that's it.
In this
I'm going to show you that the geodesic is the shortest path. Right?
So
Lambda is a parameter.
now
Right?
it's a general.
And what I want is to minimize tau. That's my wish. How do I do that? What equation do I use? Euler-Lagrange. What is the Lagrangian?
What's inside the integral?
Exactly. So this is the Lagrangian. Right?
No, just
Oh, I meant mine.
לא. אתה עושה עליו אינטגרל.
This is the Lagrangian. Right? Euler-Lagrange equation. Euler-Lagrange equation of motion. That is the action, yes, and this is the. Okay. The nice thing about this course, we'll go over half the things you've learned in most other courses of physics. You'll see if things are not clear to you, they will become clear, or you'll give up any hope. Okay, Euler-Lagrange equation of motion from variational principle. You've seen that. That's the first, I don't know, 2-3 weeks of second year mechanics. What? Is there anybody who disagree?
Is it how to
What?
form this?
What?
All these need to. It's going to look a bit ugly.
No.
To all side.
The eye of the beholder. So it's not going to get on. What's the Euler-Lagrange equation of motion? Minus d over d lambda, dl over d xi alpha over d lambda, plus dl over d xi alpha is equal to 0. Right, when this is L. What is dl over d xi? 0, right? L does not depend on xi, it just depends on the derivative of xi. Yeah? This is the Euler-Lagrange equation. This is the L d xi, 0. So we have to take the derivative of the L over the d xi alpha over d lambda, which is here. So let's take it. This is L, so we take the derivative of L. Then we get, here we get d over d lambda. L is all that to the power 1/2, so we have 1/2 L. The derivative is going to be minus 1 over c squared, which is a constant. Now I have a double here. There is a symmetry here, so I can just, let's take the derivative, put alpha, let's put a sigma, so just not to get confused. Sigma. Sigma can be either alpha or beta. Right? Since it can be either alpha or beta, then I have to do 2, so it doesn't really matter. So I have 2 eta sigma beta d psi beta over d lambda. It's equal to 0. Why the 2 is because I take the derivative once with sigma equal to alpha, second with sigma equal to beta. Not that it matters because it's anyway it's constant, so it's going to get out. Then we cancel. Right. So L, what is L really? L is the tau over the lambda. Right, so I have d over the lambda, 1 over the tau over the lambda, so I can write it d over the tau. Or here, sorry. L is the tau, 1 over the tau over the lambda, I have the psi over the lambda, everything else is just constant, so I can just remove them. And what I'm left with is d over the lambda, d psi beta over the tau. Equal to 0. Actually, it should be, sorry, there is an eta here, so it should be d psi sigma. D psi sigma over the tau because of the eta sigma beta. And when I multiply that by the lambda over the tau, and we end up d squared psi sigma over the tau squared is equal to 0.
How do you get the second equation?
Which one?
The lambda of d psi sigma over tau. How do you get?
Just right here. D over the lambda. Everything here in the parentheses.
Yes.
L is the tau over the lambda. So 1 over the tau d lambda. Everything is constant, so I can just remove it. Sigma and beta, I just write it as a sigma, so it doesn't really matter, right? So I have 1 over the tau over the lambda, d psi over the lambda. So it's d psi over the tau. Chain rule, basically. That's it. Everything else, C is it's equal to 0 anyways.
What about the square one half?
What about it?
How did you disappear?
That's here. L is there to the power 1/2, so it's 1/2 divided by L, and then there is the internal derivative.
Divided by the
It's 1/2 here. Right. I have a function here to the power 1/2. It's 1/2 divided by that times the internal derivative. Hey guys, that's serious. So you need to know how to do when I wake you in the middle of the night. What is that? What's that? That's a free motion, right? It's a free particle motion in special relativity. Promised you, right? And we just got it from the variational principle. Yeah? Don't look at me like we've all seen the variational principle, we've all seen the free falling particle motion. The important is that, okay, I just showed you this geodesic equation is not just a mathematical thing, you get it from a variational principle. Now let's do the same for general relativity. Yeah?
Can you repeat from where you started and what you got in the end with respect to what you started?
2 points, A and B. I argue that geodesic equation is the equation that you get in the shortest path. The shortest path in our concept is the minimum proper time between the points. Right? So there can be multiple paths that goes between the 2 points A and B. And I argue that the path that you'll take, the geodesic equation, will describe the path of the minimum proper time between the points. So I take this path and I perturb it. Right? That's the action. So action here is the tau. It's integral of the Lagrangian. Right? Integral over the tau. So really I wrote the tau as the tau over the lambda, the lambda. Lambda is the parameter. Right? And then I wrote down Euler-Lagrange equation, which is the equation of motion, and I just solve it. Right, so this is the L over the xi is 0, and d over the lambda, the L over the xi sigma over the lambda is what's written here. It's just plugging in L, that's all. And then get rid of all the constants. L is the tau over the lambda. So I have 1 over the tau over the lambda, the xi over the lambda, so this is the xi over the tau. And then I can simply multiply it by the lambda over the tau, and I end up with d squared xi over the tau squared is equal to 0, which is equation of motion of a free particle, okay, which I got from the claim that the path will be the shortest. Okay, that's a physics. Is that clear to everybody? That's 3 lines basically. So now I'm going to do the same, but with general relativity, right? Arbitrary coordinate system. So let's do the same with GR. So same now too. Same with the GR. So again, tau from A to B. I'm going to put it up. There's integral from A to B of the tau. There's integral of the lambda. Now I have the same, but minus 1 over c squared. Instead of eta, now I have g. G alpha beta, and now instead of psi I have the x. Dx alpha over the lambda, dx beta over the lambda to the power 1/2. Okay, it's the same equation, just now written in general coordinate system. Yeah? Nothing that should get you alarmed. What's the Lagrangian L? Everything that is written here. Right? Minus 1 over c squared, g alpha beta, dx alpha over the lambda, dx beta over the lambda. To the power 1/2. Now we have Lagrange's equation of motion, which is written here. So this term now, it looks basically the same thing as we had previously. I just write this and this equal, right? Let's move it to the other side. Right? This will be the equation of motion. Yeah? Yes, I, but x. So, the left-hand side is exactly the same as we had previously. D over the lambda of 1 over 2L, then minus 1 over c squared, and then 2g sigma beta dx beta over the lambda. Now we have to take the derivative of L with respect to x. Previously, this was equal to 0. What about now?
This is the derivative of g.
Yes, now we have the derivative of g. So it's not going to be equal to 0. Right? What?
G doesn't depend on the velocity, right?
G?
It doesn't depend on the velocity. Okay, it's okay.
No, x is the coordinates.
No, it depends. So
There are no velocities here. There are coordinates, and the coordinates change along the path.
It doesn't depend on the change in the coordinates. Just define it.
No. G depends on the coordinates.
Okay.
The coordinates can change. Right? So we have, again, we have dl over dx sigma. This will be, again, I take let's have a minus 1 over c squared, 1 over 2l. But now I have to take the derivative, so it will be a dg alpha beta over dx sigma, and what we had previously, dx alpha over d lambda, dx beta over d lambda. Right? Now, here I had what we had previously, so I can simply shorten up. Right? Here it is d over d tau g sigma beta dx beta over d lambda. Actually, it should be 1/2. Half goes here. It's 1/2. It's basically, I can cancel these two, this half and this half. 1 over 2 and that. So I have these 2 here, and that will go over to this here to make this 1/2. And here again I have L is the tau d lambda. So I multiply again by d lambda d tau, so I get another one like that. And I can write it as dg alpha beta dx sigma dx alpha over d tau dx beta over d tau. And since I multiply together, this should go over d lambda, so multiply by d lambda over d tau, and that means that here I should get d tau. I multiplied by that part, so that I can convert the lambda to tau. So one is converted because of L, and the other one is because I multiplied that. And here as well, one was because of L, and then another one because I converted lambda, multiplied by the lambda over the tau. Okay. So, yeah. Now, okay, let's write it down. So dg over d tau. So I have dg sigma beta over d tau. I write this dx mu over d tau, dx beta over d tau, plus g sigma beta d squared x beta over d tau. Right, that is these two terms. G itself does not depend on tau, it just depends on the coordinates. So if I want to derive it with tau, I derive it with respect to the coordinate, and then the coordinate with respect to tau. Minus 1/2 dg alpha beta over dx sigma dx alpha over d tau dx beta over d tau is equal to 0.
Should be the tau squared.
Correct.
Now you can replace the dx to the tau with u.
I can, but I'm not going to do it yet because I still have to worry about the since we have here a symmetry, beta really is a dummy index. Right? And we have here a symmetry. So this one I'm going to move here. So G sigma beta is for x beta over the tau squared. And this I can write as a symmetric in alpha and beta, so plus 1/2 dg sigma beta. It's new, I'm going to change that to alpha. It's a dummy index. Right, so I can do that. dg sigma beta over dx alpha. Then I'll have dx alpha over the tau, dx beta over the tau. Now again, I can change that since this is a dummy index. Right, you understand what I'm doing here? Can be a bit, take a few seconds to follow what I'm doing exactly. Now, beta is also a dummy index. I can replace it with an alpha and mu with a beta. The alpha, this will be a beta. So plus dg sigma alpha over dx beta, half and half. This is because the symmetry here. This term here is a minus dg alpha beta over dx sigma. I already have this dx alpha, dx beta is equal to 0. Right. The only thing that is left is to multiply by the inverse metric. Right? G sigma the rho. I'm going to change that into rho. Get less confused.
What? How?
It's a dummy index. When it's a dummy index,
Okay.
when it's a dummy index, I can do what I want. Just right. Then I'm left with d squared x rho over d tau squared plus gamma rho alpha beta dx alpha over the tau dx beta over the tau equal to 0. Or, if you want, we can do du rho over the tau plus gamma rho alpha beta u alpha u beta is equal to 0. What is that? This is the geodesic equation. Cool, right? This is geodesic. May take a few seconds to digest. Look, I think by now you understand that just sitting in the classroom and following will not get you too far. You have to actually go over that quietly at home. Slowly make sure that you understand where all the indexes are going. But this is simple, not too much. Just a little bit of hand waving. There's no really hand waving. I just allowed myself to change the pieces. Yeah.
When you get two terms, you've got a g derived by x to the alpha and g derived by x to the beta. How did you get two terms, not one? You had one term in the
Half. It's just symmetric. Yeah. This is 1. That's half. Just use the symmetry properties. Yeah.
I'm just confused with we changed lambda to tau and you multiplied the lambda to the tau, but
Yes.
how is the
Because there is divide by L. There was one over L here, and L is the tau over the lambda. Okay. So once I have the tau over the lambda, so 1 d over the lambda, 1 over the tau over the lambda. It's 1 over d over the tau. And then for the second one, I multiplied by the lambda over the tau. Both sides of the equation. photons? What about them? Same. What will be the only difference?
Lambda, not
I cannot use tau because the tau is 0 for the photons. So photons travel along what's known as null world line. Tau is equal to 0. So just write down the path as x alpha is x alpha of lambda. Photons path. And the geodesic equation is d squared x rho over g lambda squared is equal to minus lambda rho alpha beta dx alpha over the lambda dx beta. Okay. Cool, isn't it? Questions? At the end of the day, it's not such a terrible derivation. 1, 2, 3, 4, 5 lines. Can do. Okay, now comes the fun part. Unless you have any further questions about this derivative. I don't need to tell you, right? Go over that at home. Make sure that follow that at home. Okay. Okay, the fun part, the Newtonian limit. Now I'm going to argue. This looks quite abstract, but at the end of the day, this describes what? It's freely falling. So I'm going to argue that in the appropriate limit, which is called the weak field limit, we're going to retrieve back Newton. It would be quite sad if we didn't. Right. You have to retrieve back Newton. So let's see. To give you a little bit of feeling how these things really work in reality, practically, I would say that's the right word. Of course, there is one thing which Newton doesn't have, and Einstein does have, which is what? It's written here.
Einstein notation.
Physics notation. What's the key difference between Einstein? Just write it between Einstein and Newton. What?
Photon is mass.
What?
Photon is mass.
Photon is massless, yes. Photon is massless. And what?
No.
So what if it's massless?
The speed of light is finite. Newton.
Newton didn't refer to that. It's conceptual. What concept?
Spatial.
Conceptual. It's written right here.
Time dilation.
It's one of the conceptions, but not what I'm referring to. It's written right here. What?
That there's nothing absolute.
The Christopher symbols.
What's conceptual of Christopher's symbols? It's a symbol.
The concept of curves.
No.
Non-infinite.
Okay. When you feel gravity, right? What happens to you in a gravitational field? Yeah, you accelerate, right? Change your motion. What happens to a photon in a gravitational field? According to Newton? Nothing, right? Photon will just keep on moving in a straight line. Photon has massless, right? And so according to Newton's universal law of gravity, it is not affected by mass. You can say Newton said, right? Gmm over r squared, right? So a photon does not feel a gravitational force according to Newton.
But you convert Newton's law of rotation to acceleration, and then you put the photon, you can get something.
According to Newton's universal law of gravity,
But it also doesn't have mass, so it doesn't
right,
need, so
it does not have mass,
so you can
so
accelerate
it does not
without-
accelerate in a gravitational field, right? It just moves in a straight line. A photon, according to Newton, is not aware of the fact there is a gravitational field. It's completely ignorant to it, the same way as neutrons are not aware of the fact there is an electric field. They don't care, they just pass through it, right? Because they have zero electric charge. So a photon has zero electric mass. But according to Einstein, which is right here, the photon would be aware of the presence of a gravitational field. Right? The trajectory of a photon would be affected. We will discuss that down the line. But it's a conceptual difference. Yeah? Okay, so Newtonian limit. Newtonian limit. It's also called weak field approximation. What we're going to do now, we're going to write down the geodesic equation in the weak field limit. Geodesic equation, which is the motion of a particle. In the weak field limit. So first of all, what does it mean weak field or Newtonian limit? Weak field and Newtonian limit is the same. What is a Newtonian limit? I cannot hear.
Low speed.
Low speed, that's correct, right? So particle moves slower than very slow relative to the speed of light, right? So slowly moving particle. Two. 1 second. Why? What's two? So okay, that's a bit more tricky. Yeah, nearly flat space. Very good. Means a weak gravitational field. The gravitational field is weak. It's weak. What does it mean weak? It can be considered as a small perturbation to Minkowskian space. And the third one, which is also related to that, is that the field is static, it's not changing in time. So, slowly moving particle dxi over d tau is much smaller than c dt over d tau. That's the meaning of slowly moving particle. Okay, beta much more than 1.
dt to the tau?
dt over d tau. What does it mean about the geodesic equation?
Do you really need this negative t to the tau?
Exactly. So geodesic equation, d squared x, x, I'm going to change the indices in a second, over d tau squared plus gamma rho alpha beta dx alpha over d tau dx beta over d tau is equal to 0. Now, if dxi over d tau is much smaller than dt over d tau, then I can basically ignore everything here except from the 0, 0. So I can write it as d squared x, I change it for mu, so let's put mu. X mu over d tau squared plus gamma mu 0, 0. And then I have dx 0 over d tau twice. So this is just c dt over d tau squared is equal to 0. There are other terms, but they're very small, so I can neglect them. Yeah? Hey guys. Okay. Now, we said that the field is static. What does it mean that the field is static? What? All the time derivatives vanish, right? So, all time derivative of g mu nu vanish. So, gamma mu 0, 0 is 1/2 g mu lambda d0 g0 g lambda 0 plus d0 g0 lambda minus d lambda g0, 0. What is d0 g lambda 0? What's the notation? This is dg lambda 0 over dx 0, right? Remember that notation. But you get used to it very quickly because shortly we're going to dismiss it to a more complicated notation. Yeah? So we said this is anyway equal to 0, no time derivative, they vanish. So we have a minus 1/2 g mu lambda d lambda g0, 0. Then we said gravitational field is weak. What does it mean that it's weak? What does it mean mathematically that it's weak?
G mu nu is eta mu nu plus something.
Very good. That means that g mu nu we can write as eta mu nu plus h mu nu, where h mu nu is much more than 1. All components of this h. Okay, in absolute values, of course. That's the meaning of weak. Yeah. So with the inverse. Yeah, Taylor expansion. I can do that. It's small perturbation. Yeah. And h mu nu is delta function. It's eta, sorry. It's 2 eta function. So, what do we have here? So, gamma mu 0, 0 is minus 1/2. G is h is eta plus some correction, which is small. So I can just write this eta mu lambda. And then the lambda, what would I write here? H00, right? Because what is eta 0, 0? It's constant, so it's if I take the derivative, I get that. H00. So from the geodesic equation, right? This is the geodesic equation, right? This is what we started from, right? After doing that, we got d squared x mu over d tau squared is equal. We just move it to the other side because of a minus here, 1/2 eta mu lambda d lambda h00 c dt over d tau squared. Now, if we take lambda equal to 0, what is d0 h00?
0.
Why?
It's not dependent time.
Yes, because the gravitational field is static.
Right.
So what do we get?
The gradient.
What do we get? D squared. So I have here eta mu lambda equals 0. So eta mu have to be 0, otherwise everything is going to be 0 anyway. So I get d squared x 0. What is x 0? T over d tau squared is equal to
Half minus half.
Minus
the 0.
0.
yeah? Which means what? dt over d tau is constant. So the weak field, proper time and time are the same, which we're used to from Newton. Yeah? What about the space-like component? Let's see. I'll write down. Space-like component, we have d squared xi over d tau squared is equal 1/2 c dt over d tau squared. I have an I here, so it has to be di h00. So I can divide that by 1 over c dt over d tau squared. That just means that I can write it as 1 over c squared d squared xi over dt squared. A little bit cheating, but you'll forgive me for that. 1/2 di h00. Does that ring a bell? This equation? What?
H0
Equation.
Yeah.
Of wave.
The gradient of just the potential and
Very good.
with the minuses and stuff.
Exactly. Very good. So that means that I can write down h00 is minus 2 phi over c squared. What is phi?
Gravitational potential.
Gravitational potential. Right? Minus gm over r. And if I write it like that, then what do I get? I get d squared x I over dt squared is equal to minus di phi, derivative of the gravitational potential. So what did we get if you wrote it like that? That means that G,
How do we find big phi?
what?
Ah,
Gravitational potential. Magic? Still kind of, you understand that there is something to it, but you're not sure what. Guys, you have to, I'll put my lecture notes today online, together with the next program. So you have to go. There's no, you don't have alternative really. I mean, you do. Go to the textbooks and read it. But what's written here? G00 is minus 1 plus 2 phi over c squared. remember I told you, G would act as the gravitational potential. So when I assign, this is physics, right? This is, I assign G, remember, we, look at the logic. We derived the geodesic equation for arbitrary coordinates, right? It was a completely mathematical derivative that we did, nothing to do with physics. Now today we went into physics. We said, okay, we can derive it from the principle of this action. And what we're doing now is saying, okay, if I am associating with G, this is physics, right? Gravitational potential, then I retrieve back in the weak field limit Newton's equation of motion. That's already assigning some physical interpretation to G. Okay, so not the borderline between physics and math. And voila, this describes under this limit, the weak field limit, correctly the motion of a free particle in a gravitational field. Is that clear to everybody? What we're doing here? The math is not that difficult. It's the first time you see it, I believe. Is there anybody who saw anything like that before? Where?
Question.
What?
Question.
Where did you see?
Physics. In the physics competition.
Physics competition?
Yes.
What competition?
IPHO.
What?
IPHO.
What is that?
International Physics.
Okay. I cannot assume, right? But this is if it's the first time that you're seeing this type of equations, it takes a little bit time to digest them. So don't be worried about it, but do spend the time. But we are retrieving back Newton, which is quite good. Questions? No? Okay, we have time, which is good. So I'm going to start a new subject. If you don't have any questions, when I erase that, I'm going to start something.
You transform from G mu lower index to upper index.
It's the inverse.
But H, how do you transfer? If you multiply G mu nu by G lower and upper, how does it work? Because unless you get an I from this, delta from this, and they cancel out or something.
Yeah. So just do it with. There's nothing really to it. Yeah.
What about the other indexes? H.
What about them? They all got 0.
Yes. What would change it if the gravitational field wasn't static?
When? We'll get there. By the time we'll get there, this will look very easy to you. Okay, we'll get there. One step at a time. Okay. Vectors and tensors in curved space-time. Remember that we asked 2 questions. What were the 2 questions? This course basically addresses 2 questions. Which are they? You're listening to me? What are the questions? What? Right. One is, how does the existence of mass curves by x in such a way that it curves in space-time? And the second is, how how, given that the space-time is curved, how do we describe the motion of a particle in curved space-time? How do we? That's the question. Right? Just answer the second question. Okay, say the answer to the second question is simple. It's a geodesic question. The answer to the first question is more demanding. And we're going to start now getting the tools needed to answer that question. Okay. So, how does the presence of mass or energy occurs space and time? Before we can answer this question, we need to describe physics in curved space-time. In order to describe physics, we need to be able to describe vectors and tensors. Why are we interested in vectors and tensors? Because of another principle. This course is full of several interesting principles. And this time it's called the principle of general covariance. So basically, we want to understand or write the laws of physics in arbitrarily curved space-time. Let's say we have a physical law that we discovered, or somebody else discovered for us, and we would like to adapt this law to the general framework. How do we do that? So for that, we have this principle of general covariance, which says the following. Consider an equation that describes a physical law in flat space-time. Normally, how do we write the equation in physics? They will consider, well, what do you have in equation in physics? What do you have? Mostly. You have partial derivatives. Most of the, if you think of it for a second, most of the equations that you know in physics will contain some sort of partial derivative. Yeah? Think of that. Yeah? Most of them. Now, according to the principle of general covariance, according to the equivalence principle, according to the equivalence principle, this equation will hold in the presence of gravity provided it is generally covariant which means it preserves its form. Under general coordinate transformation. principle of general covariance. Which is, okay, let me second. I have an equation. I know it is correct without gravity. I argue that if this equation, now I add gravity to the system, and I look at the equation and it looks the same. The same equation, right? It looks the same. Then I argue that it is correct in the presence of gravity. Okay? That's the principle of general covariance. Why? In other words, there's something quite deep here. What it really states is that the equation does not depend on the coordinates. Okay? And that's exactly what we want from a physical equation. Because remember, we spoke about it at the beginning. The coordinates is something that I choose, because it's handy for me. But the physics doesn't know anything about my coordinates. The distance between here and Mars is independent of whether I measure it in kilometers or in miles. It's good for me to know, but not for the distance. We know why I said that. Why I gave this example. Don't know. There was a famous story. They said there's some spaceship to Mars. It was crashed because there was a joint mission between Americans and Europeans. But they realized why it crashed, because the Europeans were counting in kilometers, the Americans in miles. So there was some mismatch there, and it crashed. True story. Yes.
What does general covariance mean?
That is what it means. The question is generally covariant means that it preserves its shape, its form. It has the same form.
What's its form?
Structure. The way it is, you write down the Maxwell's equation, whatever. It looks the same, it means it's correct. Right? Why? Now, I argue this follows from the principle of equivalence. Right, so, proof. Right? So, let's say that we have arbitrary gravitational field. Assume arbitrary gravitational field. Right? Now I have an equation that satisfies both conditions. I have an equation, consider an equation that satisfies 1 and 2. Right, this is 1, this is 2. Now, the second condition says that if the equation is correct in one coordinate system, it will be correct in any coordinate system. Right? And in particular, it will be correct in the freely falling coordinate system, which we can always find, because that's what the principle of equivalence told us. There is always a freely falling. So this is also correct, which means that both of them have to be correct. Right? From 2, if it is correct, in one coordinate system, it is always correct. One equivalence principle says there is always a coordinate system, a freely falling coordinate system. system. This equation is correct in that system. It is correct in that system. Therefore, anywhere. Therefore, any system. Again, as I said, this is a consequence of the equivalence principle plus the demand that the equation, non-equation will be depending on the coordinates. From here, it explains why we spend so much time dealing with vectors and tensors. Why? But what do we know about vectors and tensors? What?
It helps us to convert from one.
Exactly. We know how to transform them from one system to another system. Right?
Provided we are in the same tangent space.
Yeah. This is true.
So we don't know how.
So-
we don't know yet how to move them from one tangent space.
It's true. That's true. And we have a major problem here. You're right. What is the problem? We said most of the equations that we know in physics, I think all of them, are composed of what?
Time.
Derivation. Partial derivatives. No, not. I'm thinking of space. Partial derivatives. So, to do a partial derivative, you need to be moving from one point in space to another one to see how the vector or the quantity or interest in it changes. So we need to know how to do that. So basically what we're going to do in the next, I don't know, 2 weeks, maybe week and a half, 2 weeks, whatever it takes, so as long as it takes, is to generalize the notion of vectors and tensors, which we introduced truly only in flat spacetime, so that we can use those in any arbitrary curved spaces. Generalize the notion of vectors and tensors to arbitrary curved space-time. I'm going to make a statement. I don't have time. The time is running out, so we'll finish in a few minutes. But since that's what we're going to do on Sunday, I'll let you some things to think about over the weekend. I'm going to write vectors in curved spaces. What are they going to be like? What are vectors in curved spaces? What?
They will be associated with some tangent space.
They will build a tangent. All the vectors will form a space, which is a tangent space. Yes, but
we need to specify.
I'm going to make you the following statement. Vectors are directional derivatives. What is a directional derivative?
Gradient times already.
What?
Gradient times the derivative.
Nearly gradient?
Gradient of a function, scalar product with the.
It's the gradient times the direction. Just the definition of the derivative just means because space is multiple directions. So you choose one and just
You're around
one
it.
direction.
You're nearly. What is the directional derivative?
How function changes when you move to a particular direction.
Yeah. Okay. So what do I need to
Maybe
do?
because they're also in the time, because there's also time in this space.
Okay, what derivatives do you know? You know full derivative.
Gradient.
You know partial derivative. What is the directional derivative? It's a generalization of the idea of a partial derivative, basically. But what is a partial derivative? Right, you put a set of coordinates. Right, you put a set of coordinates, x and y, and you say, well, oh, x1 and x2. Right, we're doing physics here. And then you're saying, okay, I have a function f, and I have it at a certain location, right, x1 and x2, and I have a partial derivative, meaning I can look at f, how it changes when only one of the coordinates change, right? x1 changes or x2 changes, right? So directional derivative.
Linear combination.
No, remember,
Along line.
along the line, right? The coordinate is something.
The same.
The coordinate is something which I put by hand, right? It's my coordinates, right? But I can put a line, right? So I can say the vector would be the directional derivative is the partial derivative along that line. Makes sense, right? Now we're going to do that more properly. I'll give you the full mathematical definition, which is a bit. And what is the problem really? How am I going to solve it? We said vectors belong to a point, tangent space at a single point, right? Now, how can I do these things? What allows me to do that thing?
It's locally flat. So
Good, it's locally flat, right?
The tangent space.
And that for that we need to go over the concept of a manifold. Now we need to actually define a manifold, and I am not going to do it for you because I don't think it's really necessary. Actually, I'll ask either we do it in one of the tutorials or we do it. I will do it if you really insist. The reason why, because it's heavily mathematics, and I don't really think it's necessary. Because intuitively, I think you can get the concept without the need to go. There are. I have it. I wrote it down. It's all written in an appendix. There are something like 6 or 7 different definitions which you need to follow. Mapping, map composition, vertical map, smoothness, open ball, open set, chart, coordinate system, atlas, and then at the end you can define one. There are several things which you need to define. It's not so difficult, but I don't think it's necessary. The important thing for a manifold, right? It's a space which is locally flat in each point. It doesn't contain any spikes. It's not a porcupine. This is not a manifold. But a sphere or a torus, right? Or a bagel, right? These are legitimate manifolds, right? That, by the way, is called, well, genus 0, genus 1, genus 2. Right? Manifold has holes in it, right? But it's legitimate manifolds. A manifold, for me, the way I think of it is a space that is not Euclidean space globally, but locally it is. When you go every point, when you zoom in on that point, it will become flat. Okay, so this is a manifold. Now there is the complete mathematical definition. I either give it to you or not give it to you. That depends on how much time you have and how interest you have in that. But since this is a physics department, the important thing is to realize that. Now, since we're running out of time, I'll just write it down. And a manifold, I'll write it down here, a manifold. Of course, it's n-dimensional, right? N-dimensional space. Dimensional space that near each of its points resembles n-dimensional Now give me that. Is there anything that is not?
Monday is not. Monday.
Monday 3 to 4.
Are you talking about next week?
I don't know yet. It's a bit more complicated than that because, wow, until 8 p.m. everybody's, wow, it's very busy. No, we need more than that. No, it's also a matter of finding a free lecture hall, free place to talk. Well, that's the entire semester. You're full until 8 p.m. Is there anybody that only has like a partial semester? Everything you filled in is full completely. Wow. Okay, let's see what we can do. I'll check and come back to you. Only Monday 3 to 4.
When is next week?
What?
In 2 weeks we have
In 2
a
weeks we
seminar.
have seminar. The seminar starts in 2 weeks. This will be.
It's long.
That's also not full.
Yes.
It doesn't give us too much time. Wow. Could be a problem. We will need to find some time to compensate. Okay. Any further questions about what we said? Is that clear, guys? What's your next problem set? And yeah, by now I cannot assume that you know the things. You got the idea, right? We're not playing games here. You have to actually do it. Work it out until things get clear in your mind. All right? So see you on Sunday. Have a nice weekend. תן לו, אין לו פרופ.
אבל יש עוד כאילו, גם משלחתי.
פה, טופולוגית, אתה לא יכול להעביר את זה לזה. אתה יכול להעביר את זה לקוסטייט, אבל אתה לא יכול להעביר את זה
אני יודע למה, מה זה גנוס? אני יודע שהוא נשמר ויכול לעבוד, אבל למה, כאילו...
יש לה אפס קוראים, אין לזה...
הכוונה היא שיש לו גנוס אפס, או שככה קוראים לה?
כך קוראים לזה, גנוס אפס.
אבל גם, כאילו, למה לפעול כך כדור משטח?
השאלה מה זה משטח?
שור.
כללי. בסדר, זה לא... זה לא מחר
יש גנוס אפס.
זה לא מחר, גנוס לא מגדיר לגמרי.
אוקיי, הכוונה שיש לו גנוס אפס, לא שהוא כאילו, זה לא שזה הגדרה...
לא, זה לא הגדרה של גנוס.
אני שהתכוונת של יריעה הזאת קוראים גנוס אפס.
טוב,
נראה על כל סתם.